All right, welcome everyone. Today we're diving straight into the deep end of malware and modern attack technologies. And look, if you're picturing a simple computer virus from the 90s, I want you to just wipe that slate clean. We're talking about something else entirely. Complex, sophisticated, and intelligent adversaries. Let's get into it.
So here's our game plan. We're going to start by putting on our black hats, thinking like an attacker to really understand their tools and strategies. Then we're going to flip the script entirely and step into the defender's shoes to figure out how we can possibly fight back against these things. First things first, we have to move way beyond the textbook definitions. To really get a handle on modern malware, you've got to appreciate the sheer scale and sophistication we're actually up against. Okay, the absolute key thing to grasp here is that modern malware isn't just a single file. It's not one piece of code. It's an entire operational ecosystem. Think of it less like a digital disease and more like a commercial product. Seriously, it often has its own support infrastructure, it gets automatic updates to evade new defenses, and it can hide anywhere. Anywhere in a system. From the moment your computer starts booting up, all the way to the document you're working on.
This brings up a really fundamental choice for any attacker. Are they going in with a sniper rifle or a sledgehammer? On one side, you have isolated malware. This is the sniper rifle, a piece of code custom built to hit one specific organization and go after its most valuable assets. On the other side, you've got the botnet. This is the sledgehammer, a massive, coordinated army of infected computers used for huge campaigns like DDoS attacks or blasting out millions of phishing emails. Two very different strategies.
So now let's drill down into the code itself, the actual weapon. For anyone writing malware, job number 1, 2, and 3 is to stay hidden. And to do that, they have a whole arsenal of tricks to make their code invisible. So how do they hide? Well, they have this whole bag of tricks. A huge one is polymorphism. Think of it like a shapeshifter. The malware literally rewrites parts of itself with every new infection, so it looks completely different each time, even though it does the exact same bad thing. Then there's packing. This is like hiding a weapon inside a suitcase. The malicious part of the code is all compressed and encrypted, and it only gets unpacked and revealed at the very last second, once it's already inside the system. And finally, rewriting. This is just sneaky. It's like taking a sentence and replacing all the words with synonyms. The meaning is the same, but it looks totally different, fooling any kind of pattern-matching defense. And this quote right here, this gets to the absolute heart of the problem for defenders. For decades, antivirus software worked by looking for signatures, basically a digital fingerprint of known bad code. But if polymorphism means every copy of the malware has a brand new, unique fingerprint, how can you possibly have a rule to catch it? It's like trying to catch a spy who has a new face and a new passport in every single city. It makes that traditional approach almost obsolete.
Okay, so the weapon is built, it's cloaked in invisibility, but how does an attacker actually deploy it? Well, it turns out there's a pretty standard playbook, a framework that breaks down an attack into a few logical steps.
And that playbook is often called the cyber kill chain. The key is that an attack isn't just one moment. It's a process. It starts with reconnaissance. The attacker does their homework, scoping out the target. Then comes exploitation, where they find a weakness and use it to get in, often through something like a malicious email attachment. Once they're in, it's installation. The malware is dropped onto the machine, giving the attacker their first foothold. This next part is critical. The malware phones home to a command and control server to get its orders. And once that connection is made, it's on to the final step. Action on objectives. The attacker can finally do what they came for. Steal data, break things, you name it.
Let's just double-click on that command and control step, because it is the absolute heart of a modern attack. You can think of the CNC server as the brain of the operation. It's the puppet master. And because it's so important, attackers go to incredible lengths to protect it. They build these complex, multi-layered networks with relay servers, kind of like a spy network with dead drops. So even if defenders find and shut down one piece of it, the central brain stays hidden and the operation continues.
All right, we've been living inside the attacker's head. Let's take a deep breath and switch sides. It's time to put on the defender's hat. We've just established that this stuff is designed to hide. So, how in the world do we find it? That's it. That's the multi-billion-dollar question, isn't it? And the answer, unfortunately, is not a simple silver bullet. There's no one magic tool. The real answer is to have a multi-layered defense that combines deep analysis with broad monitoring, looking at the problem from every possible angle. When it comes to analysis, defenders really have two main approaches. First, you've got static analysis. This is like reading the blueprint of a building. You look at the code without ever running it, trying to figure out what it's supposed to do. It's safe, but all those obfuscation tricks we talked about can fool you. Then you have dynamic analysis. This is like detonating a bomb in a controlled blast chamber. You run the malware in a safe environment, a sandbox, and you just watch what it actually does. This cuts through the obfuscation, but you only see the behaviors that get triggered in your specific test. To really know what you're up against, you absolutely have to do both.
And that same idea applies to how we monitor our systems. We need visibility at two different altitudes. There's host-based monitoring, which is your boots-on-the-ground view. You're looking closely at a single computer. Are there weird processes running? Have critical files been changed? Then you have to zoom out to the eye-in-the-sky view, which is network-based monitoring. Here, you're watching the traffic flowing between all the machines. Are they talking to suspicious servers? Is data leaving the network when it shouldn't be?
Now, here's where we get into this constant, fascinating cat and mouse game. For that dynamic analysis, where we run the malware, there's a fundamental trade-off. If you run it on a real physical computer, what we call a bare metal system, it's very hard for the malware to know it's being watched. But it's also very hard for us to see everything it's doing. On the flip side, you can use an emulator or a virtual machine. This gives you godlike visibility. You can inspect every single instruction. The problem? It's much easier for the malware to realize it's in a fake environment. And get this, a huge percentage of modern malware is environment aware. If it thinks it's in a sandbox, it'll just play dead and do nothing at all.
Okay, for our last section, let's talk about the absolute cutting edge of this conflict. For years now, defenders have been turning to machine learning and AI to find threats that traditional methods miss. But this has opened up a whole new can of worms, a completely new battlefield. This right here is one of the most pressing questions in all of cybersecurity today. Just think about it. If your primary defense is a smart algorithm that learns from data, a clever attacker won't just try to sneak past it. No, they'll attack the learning process itself. They'll try to fool the model, to poison its mind. And this has created a whole new field called adversarial machine learning. So what do these attacks actually look like? Well, they're incredibly subtle. You have techniques like polymorphic blending, where an attacker carefully crafts their malicious payload, so that statistically it looks identical to safe, normal network traffic. The AI model just looks right past it. Even scarier is data poisoning. Here the attacker finds a way to inject bad data into the model's training set, effectively teaching it that malicious behavior is actually normal. They corrupt its understanding of reality. They can even inject totally meaningless features into their attacks, tricking the model into thinking those features are important, which gives the attacker a backdoor to bypass the model whenever they want. And this quote just nails it. We've all heard that phrase, garbage in, garbage out, and that is the Achilles heel of machine learning. A model is only as smart or as trustworthy as the data it's trained on. If an attacker can pollute that data, if they can poison the well, then the entire defense could be compromised from the inside out. And this has kicked off a brand new, high-stakes arms race between building more robust AI models and attackers finding new, clever ways to fool them. So I'll leave you with this final thought to really chew on. As both the offense and the defense become more and more automated and intelligent, are we rapidly heading toward a future where cyber conflicts aren't really fought by humans sitting at keyboards? A future where battles are won and lost in microseconds, decided not by human strategy, but by the emergent, adaptive behavior of dueling algorithms? It's a pretty heavy thought. Thank you for joining this explainer.